Today's speaker, Dr. Jing Liu. Dr. Liu is an application scientist with NanoMEGAS USA, where she has responsibility for applications, training, and customer support. The title of her talk is Extending TEM Capabilities with Scanning Precession Electron Diffraction. Here's Jing.
All right, thank you, Robert. Thanks everybody for tuning in to the first of our webinar series. Before we get started, allow me to share with you something, someplace I think is pretty neat to visit sometime when you get a chance. So this photo was taken in 2016 somewhere in the US. The caption is, "The force is strong." It is my hypothesis for the mysterious movements of those rocks on a super flat, dry lake bed, and they will leave miles of trace behind them. So it's quite neat. And the location that the photo is taken from will be revealed at the end of the webinar. So stick around. All right, back to work. Like Robert mentioned, today I'd like to share with you how scanning precession electron diffraction could extend your TEM's capabilities. Let's start with some examples. The first example is ASTAR orientation mapping of a polycrystalline copper material along the Z direction. Z is perpendicular to the screen, pointing outward. So the orientation is color-coded and the legend is shown on the right. So let's take this large red. Green, for example, is oriented close to the 001 zone axis. Now, the beauty of a map like this is that grains with size ranging from a few nanometer to a few hundred nanometer are reliably indexed over a pretty flexible field of view. So here we have 1 micron across. So we have high reliability indexing, high spatial resolution, and flexible field of view. The second example is Topspin stream mapping of a 2D commercial transistor. So we have P-type MOSFET here, actually. So shown on the top left, we have the virtual stem image formed for survey purpose, specimen navigation. So this is about 3 micron across. So the reference pattern can be chosen anywhere within the field of view. So it's typically chosen in the substrate region, silicon here. And then the stream map was acquired from the device region. So shown here on the right, we have the principal string components X and YY. And so you can see the source and drain structure and the channel region in between. So string engineering is used to enhance the mobility of the carriers. In this case, the mobilities are whole, so we apply compressive string to enhance the host mobilities. Now, a stream map like this, precision can be pretty high, up to 0.02%. That's 2 to the 10 to the minus 4. Now, the application like what I've shown above, high reliability orientation map or high precision stream map, can be obtained from most what I call commonplace TEM specimens and of most modern electron microscopes, provided that precision is implemented to the microscope. Now, this is where NanoMEGAS solution comes in. We can equip effective and efficient precision to your TEM. So you provide the microscope, and the microscope is typically operated at a fine quasi-parallel beam condition. And then NanoMEGAS system would introduce synchronized beam precession and scanning. It's effective because it works with most modern microscopes. It's efficient because we have high frequency precession. And then we have automated precession alignments, which is important because if you want high spatial resolution, you want the precession alignment in the real space to be pretty good. And then we also provide automated data analysis tool sets. Shown here, it's the standard configuration of our system. So let me walk you through based upon user input, scanning and precession signals are generated. The digital signal is generated and then sent to a universal beam scanning and precession unit. So this unit would convert the digital signal into analog signal and then send it over to the microscope. So the electron beam will go through the precession and scanning interact with the specimen and generate precession electron diffraction patterns. So the diffraction pattern are collected using various kind of cameras or detectors. Currently, we support several models of external camera, some direct electron detectors, and some in-column cameras. Virtual STEM images can be generated for survey purpose or specimen navigation purpose. And a 4D dataset is acquired here, just like all 4D STEM techniques, where for each X and Y position of the 2D scan, you get a 2D diffraction pattern. However, with the implementation of precession, the data here, the diffraction pattern is actually more faithfully and more readily reflect the orientation or string information, and which makes the automation of the reliable data analysis possible. So let me explain why. So we have to understand how precession improves the quality of the diffraction pattern. Speaking of precession, we have to start with electron crystallography, where crystal structures are attempted to be calculated based on diffraction pattern acquired in the reciprocal space. However, the traditional nanobeam diffraction struggles severely from two aspects for this purpose. So let's take this UV oriented under 111 zone axis. On the left is the experimental MBD pattern. On the right is the kinematical calculation. So the first aspect of the struggle is dynamic effect. The dynamic effect is the result of the strong Coulombic interaction between the electron beam and the electrostatic potential of the specimen. And the consequence of that is the intensity of certain reflection in the diffraction pattern is no longer proportional to the square of the structure factor, but also the intensity of one reflection depends on the structure factor of other reflections. So this just makes it a little bit difficult to deal with. The second struggle is that it is difficult to acquire a complete set of diffraction because typically only low-order Bragg diffraction signals are available. So this makes it quite difficult to calculate crystal structure without any prior knowledge of the structure itself. And this is precisely what precession was introduced for to overcome. So let's watch a video. We start with nanobeam condition of main, excuse me, allow me to go back. So we start with nanobeam condition of the main structure oriented at 111 zone axis, and then beam precession is introduced. As the precession angle increase, you can see higher and higher order Bragg diffraction signals are excited. Furthermore, the intensities start to deviate from the dynamic behavior and start to exhibit some kinematic-like kind of behavior. Now, patterns like this are a lot more suitable for structural determination. And to implement precession in concept is quite straightforward. So we start with the nanobeam condition. Quasi-parallel beam would interact with a specimen, generate diffraction pattern, which has strong dynamic features. You can make out some Kikuchi lines as well here. It takes two steps to implement precession. The first step occurs above the specimen plane, where the electron beam is tilted away from the optic axis and then back such that it will pivot around a fine point on the specimen plane. This is quite crucial for high spatial resolution applications. And the diffraction pattern you obtain consists of rings because, which is a consequence of the beam rocking. The second step occurs below the specimen plane, where the counter precession is applied such that the direct beam and each individual Bragg diffraction spots are converged back to their respective selves. So as the beam rocks around the optic axis, the intensity is integrated, and with the dynamic effect largely averaged out, what is left is kinematic-like kind of pattern, which is quite similar to the computation based on kinematic simulation. Now let's put the MBD pattern on the left and PD pattern on the right side by side and compare with the kinematic calculation. You immediately notice the striking difference between the NBD pattern and the simulation. And also you notice the striking similarity between the PED pattern and the simulation. So PED pattern like this will make the structural determination a lot easier, even without any prior knowledge of this crystal structure. So the higher the precession angle you use, the more dynamic the intensities are. And as it turns out, even with precession angle of 1 degree or lower, which is a lot lower than what those are using, those typically is about 2 to 3 degrees. So even with 1 degree or lower precession, the diffraction pattern quality can still be significantly improved in the same aspects, which are first, the dynamic effects are averaged out to a certain extent, and second, higher order Bragg diffractions are excited and recorded compared to those patterns that without precession. Now, it's precession patterns like this makes the data analysis more easy and makes the automation of reliable data analysis possible. So now we learned the power of precession. Let's revisit the two applications we mentioned at the beginning. So we start with precession-enabled orientation and phase mapping. Here, enable is the key word because it equipped this technique with unique advantages. It has general applicability because what this means is it can be used reliably on most TM specimens that has a little bit thickness variation, a little bit buckling, a little bit damage. And this is because the precession average out dynamic effect to a certain extent. So it cleans up the pattern a little bit. You have little or no Kikuchi lines also. The higher order Bragg diffraction signals are excited and recorded. Those spots are more sensitive to orientation, changing orientation. So it enhanced the indexing reliability. But this enhanced reliability also is a result of a effective and efficient indexing algorithm that has been pioneered by Dr. Edgar Roch in Grenoble in France. Okay, let's dive into this technique. For those of you that are not familiar with our ASTAR orientation phase mapping technique, it's essentially similar to EBSD maps obtained in a TEM in the sense that you obtain orientation or phase information. But our technique works largely complementary to the SEM technique because we work at different regimes, much finer scale with higher spatial resolution. And also this is ours is a transmission technique compared to SEM as a surface technique. And speaking of high spatial resolution, here's a fine example of an orientation map. It's a Z along Z direction of a copper interconnect sample. So copper interconnects are the fine metal wires within integrated circuit that connect devices, and they serve to carry current. So they're microstructure. I guess in this case it's nanostructure because it's the grains are so fine. The nanostructure would influence their resistivity capacity, so it's quite important to characterize what structure you get. The orientation reliability parameter I'll explain a little bit later in detail. So let's take a look at this area enlarged down here. We can obtain a disorientation line profile across the region. So you can see a 60-degree jump across this region. So this is a 2 nanometer twin structure, comfortably resolved by our technique. Shown here is an example of a simultaneous orientation mapping shown on the left and phase map shown on the right. So here we have a total of 4 phases being resolved. Now structure maps like this is quite important for researchers to understand what kind of structure they're getting to further fine-tune and optimize the performance of polycrystalline cadmium telluride material. So whether it's orientation map or simultaneous orientation and phase map, the underlying indexing process is the same, and it goes like this. So for a given crystal structure at a given orientation, we can calculate a template based on the kinematic assumption. And this orientation is one of the many allowed orientation as bounded by the crystal symmetry. So this entire orientation space, you can call it, can be sampled discretely, typically with the step size about 1 degree per step. So you end up with a pool of templates. Each step or each orientation, you have a template. So when the experimental pattern comes in, it'll be compared with the pool of templates using this index parameter Q. And this Q parameter serves to compare the similarity between the experimental pattern and the template. The more similar the template is to the experimental pattern, the higher the Q value is. And then the template that has the highest Q value is chosen as the indexing result. Amorphous phase can also be indexed in a similar fashion. So shown on the top is a precession pattern obtained from amorphous region of this nickel titanium structure. And a ring-like template can be constructed to mimic the diffraction signal obtained from the amorphous region. So shown on the right is the obtained phase map where the amorphous phase and the crystalline phase are mapped out. So indexation is only the first step. And after that, we can extrapolate a lot more information from the material. Let's get some examples. So here is another copper interconnect sample. At the bottom row, we have orientation maps along different directions. The direction is X is horizontal point to the right, Y is vertical point up. And shown on the top, there are a few new informations. Let me explain what those are. So the virtual bright field image is constructed online during data acquisition by placing a virtual aperture around the direct beam. So as the beam is scanning on the specimen, the intensity within the virtual aperture is integrated and mapped out. So you can see some contrast, much similar to what you see in bright field TEM images. However, the contrast is a little bit different because precession is being applied here. So dynamic effect is a little bit less. The second one, index map. Recall index is an indicator of the similarity between the experimental pattern and the template. So you can see a little bit more detail in the index map compared to the virtual bright field image. And the reason is that index value inherently is a little bit lower at the green boundary regions, for example, because at those regions you have more than one set of diffraction pattern in the experimental pattern. So it brings the index value down a little bit. Reliability is a very important parameter to introduce simply because the existing indexing algorithm determines given a pool of templates, there is always an indexation solution. However, whether that solution is safe or not, this is what the reliability is used to help judge, is defined by the index value of the second best match Q2 and the index value of the best match Q1 in such a way that if Q2 and Q1 are similar in value, our reliability will be low. So you can get an idea of how safe your solution is. So here's another example of orientation map obtained from polycrystalline silicon. So you can see virtual bright field image generated during data acquisition. The contrast is pretty complicated here. The orientation map gives you a better idea of where the grains are, what the orientation is. But we can also obtain a lot more green characteristics. Shown here, automatically generated is a green boundary map. User can define the threshold for the green boundaries. And the highlighted in blue are the trim boundaries constructed here. We can also construct other special boundaries. So from this green boundary map, the green size distribution can be extracted, or the green size raw data can be exported so that user can pull up the green size data from several maps to get a larger population for better statistic analysis. Virtual dark field images can be constructed offline because we do have a 4D STEM data set. So this is quite useful for visualization purpose. Now, because the aperture are virtual in nature and you can apply all kinds of numeric operations to it, you're only limited by your imagination. Virtual dark field image can be constructed to emphasize all kinds of microstructural features, such as dislocations. Shown here is an example of inclined grain boundaries. So it's a polycrystalline alumina thin foil sample. In the middle, we have a single aperture used to calculate the virtual dark field image that will have that grain highlighted, that if the grain scatters at this particular region of the diffraction pattern. And shown on the right, we have a series of positive and negative patterns, apertures, and used to sort of emphasize the green boundary inclination over here. Correlation coefficient map is one of my favorite tools because it gives you some insight about the through thickness structure of your TM specimen, which is quite valuable information, and it's not straightforward to get for transmission techniques. So two examples here shown on the left is the tetrahedral gold nanoparticles. The virtual bright field image shows some contrast within the particles, but it's rather difficult to make out what they are. And the correlation coefficient map nicely illustrated those are planes within those particles. And shown on the right is carbide precipitates in steel. So similarly, the virtual bright field image, you can see some blurred contrast where there's a cluster of grains. While on the right-hand side, the correlation coefficient map nicely reviews that those are actually overlapping grains. You can make out the small grain overlap with the large grain. Now, the reason that correlation coefficient map can review through thickness structure like this is because it's defined in such a way that it compares the diffraction pattern obtained from a certain region of the map, and compare it with its nearest neighbor along the scan direction perpendicular to the scan direction, so that if there is any change in the diffraction condition, the contrast will be brought out. Now, you may recall here, this is the orientation map that was sent out together with the webinar invite. So this is the orientation map of those nanoparticles. And turns out those planes are actually twinning planes. All right, so this concludes our ASTAR orientation and phase mapping section. The other application is precession-enabled string mapping. Again, because the application of precession, this technique has general applicability to most TM specimens. High precision can be obtained because the higher order Bragg diffraction signals are acquired and recorded. So they tend to move a little bit larger reciprocal space distance for the same amount of strain than their low order counterparts. We also provide effective and efficient string computation. So let's take a closer look at this technique. It is first important to clarify the definition of string we're discussing here. It is different from the material strings that a lot of people are accustomed to, in the sense that the reference can be chosen arbitrarily. Shown here the example, we have silicon and germanium, where germanium is about 4% lattice mismatch from the silicon. So germanium has a larger unit cell. So if germanium is grown coherently on the silicon substrate, what happens is within this growth plane, the larger germanium unit cell will be squeezed, such that perpendicular to the growth direction, the germanium cell will be stretched. So this is the so-called tetragonal distortion. And those with the reference being chosen in the silicon region, this germanium cell does have some strain along this direction. Now, strain like this are important to be characterized because there was strain engineering since the early 2000s for the sub 130 nanometer techniques. Strain engineering has been used for nanoelectronic structures to locally alter the crystal symmetry and band structure to achieve the desired electronic properties. So shown here on the left is a P-type MOSFET where the compressive strain is being applied to the channel region to try to enhance the hole mobility. Now, as the device structure keeps shrinking, so you need higher and higher spatial resolution to characterize those strains. And we have been working with our customers now at the lower end of the graph for the cutting edge technologies. Listed here are several commonly used high-resolution stream mapping techniques in a TEM. All of those techniques, they struggle somewhat from one or more, actually, the following aspects, namely the requirement on the specimen, the stream measurement precision, the field of view, and the easiness of data analysis. Let's take a quick look of every one of them. First, dark field electron crystallography, the precision can go up to pretty high. However, there are experimental difficulties related to bioprism, control of the specimen thickness, and you need a pretty stable microscope to have long acquisition so that the hologram contrast is enhanced. Data analysis part of the diffraction contrast, it is difficult to deal with. And it also requires the strain and strain region to be close by. So it's non-trivial. The geometric phase analysis of high-resolution images, the precision is reasonable, not super high, but this technique is super easy to implement. It does struggle with limited field of view because you do need to get high-resolution image, and the specimen quality is the better, the better. The third technique, conversion beam electron diffraction, similar to dark field holography, the precision can go pretty high, but it struggles from the experimental setup and data analysis. So it requires pretty thick specimen to see the high order Loison lines, which shifts with the strain. It requires calibration of the high tension pretty well. The host line contrast can be complicated if there is strain relaxation or there is any defect. And to correlate the host line position with the strain, typically dynamic simulation is needed. So it's non-trivial as well. And nanobeam diffraction ends up to be a more versatile technique among those because it provides a reasonable compromise among all of those. So the precision is reasonable, but it suffers severely from the dynamic effect so that it limits its application. It can only apply to specimen with minimal specimen thickness variation or minimal buckling. So no technique really has it all until precession is used for stream mapping. Let me explain with an example here. So we have a single crystalline substrate. Grown on top of that is epitaxial layer coherently grown. A and B are to position in this epi layer 50 nanometers apart. Shown on the top row are NBD pattern acquired from A and B. So you can see with 50 nanometers apart, the diffraction pattern already looks rather different. It is quite difficult to do reliable stream mapping with patterns like this. Now, with 1 degree precession being applied, the two patterns immediately are a lot similar with the dynamic effect averaging out. So you can also see that higher order Bragg diffractions are acquired compared to the NBD pattern. So with the implementation of precession, the requirement on the specimen is relaxed, and the precision is guaranteed by the higher order Bragg diffraction being recorded. The field of view is flexible because this is a scanning technique and we have synchronized scanning and precession. Now, the last piece of the puzzle is the easiness of data analysis. And this is guaranteed by our automated string calculation. So we can accommodate some beam convergence. The importance of this, I'll talk about it a little bit later. Our algorithm is also relatively immune to intensity variation within diffraction spots. So this makes the diffraction spot position determination more reliable. And the computation is pretty fast. Shown an example here is, so it takes a matter of minutes for roughly 6,000 pixel map. Shown here are some examples of the precession electron diffraction pattern obtained from external camera in A and a certain in-column camera B and C. So the diffraction spot positions are automatically identified by our algorithm, and the spot positions are marked by the red crosses. The saturated spots are not really used for the string computation. Neither are the too noisy spots. So to try to guarantee the string analysis accuracy. The accuracy of string mapping techniques is typically evaluated using a silicon germanium on silicon blanket test structure. So the structure has a known amount of germanium, and then the thickness of the layer is also known. The expected string can be simulated using finite element simulation, so it's about 1.2%. And shown on the top right is the string maps acquired using our technique. So the in-plane string is largely negligible, which is expected because this is a coherent interface. While the string along the y direction, we can get a line profile across this region. So you can see we get about comfortably within 0.1% accuracy. The string measurement precision typically is evaluated by repeated measurements of string in an unstrained region, and the reference is just randomly chosen from one of them. So here is a focus ion beam prepared a silicon substrate here. So the standard deviation of the measurement of the string shown on the right give you an idea about the precision of the measurement. So you can get 0.02, 0.03. And this is obtained off a real world specimen. I like to call them commonplace specimen because they're just a focus ion being prepared. And it's not one of those specimens you come by every once in a while with super good quality, minimal damage and all. Now, it's because of that, the enhanced accuracy and precision, we can get pretty efficient and robust string maps example shown on the right with good spatial resolution and precision over flexible field of view. Our technique can not only be applied to semiconductor materials, single crystalline materials, it can also be applied to polycrystalline materials. Shown here are two examples. One is ceramic on the top, boron carbide, and metal on the bottom, magnesium. So let's take a look at them. So at the boron carbide, the case is to study the thermal contraction anisotropy. So we have two grains. They share the same zone axis, the 1,1 bar 2,0. So grain 1 and grain 2. Those three facets, the inclination of the facets with respect to the z-axis can be measured from the orientation map. And then the string is measured, the string parallel to the facets is measured with a reference chosen from within the grain 1. Remember, we are working in the elastic regime. So the sign of the string can be calculated based on some model simulating the thermal contraction anisotropy, and the measurements agrees well with the model. At the bottom example, the polycrystalline magnesium is used to study the elastic field around a low-angle grain boundary. It's extending from the top left to the bottom right, and some dislocations also. This show at the bottom left is the construction of virtual dark field image. Recall this is one of the tool in the ASTAR orientation map. So because you have a 4D stem data set, you can use virtual aperture to build VDF images. So you can work out those planes are actually basal planes based on the G.B visibility rule. Now the elastic string field around the dislocations are mapped out here. A is chosen from this dislocation and B is chosen from this one. So the string value agrees with the elastic solution for the string field across the single dislocation. So it follows a 1/over distance decay as you move away from the core. So those are the demonstration of concepts. how you use strain in a polycrystalline material. The key point is the reference has to be chosen from the same grain. Now, I mentioned that our algorithm can accommodate some beam convergence. The importance of this is it has to do with the probe size. So show here on the right are 110 silicon diffraction patterns and their probe size in the inset at different beam convergence. So for MBD, you have a more parallel beam, and the consequence of that is in real space, the probe is rather fat. If you can live with some beam convergence, increase it a little bit, you can see in real space, the probe size is a lot smaller. So essentially, you're dealing with a diffraction limited probe where the probe size is inversely proportional to the beam convergence. Now, with our algorithm, it is possible to accommodate some beam convergence and opens up possibility for higher spatial resolution. Okay, so this is a summary of the advantages of the NanoMEGAS precession electron diffraction technique. The reliability is enhanced because precession helps to average out dynamic effect. So you can, the data is more immune to specimen buckling, a little bit thickness variation is okay. And the Kikuchi lines are got rid of. The data analyzability is pretty high. It's because the diffraction intensity is quasi-kinematical, so it makes the automation of a reliable data analysis possible. The analysis accuracy and precision are enhanced because higher order diffraction spots are acquired, and those spots are more sensitive in changing orientation or strain. And the high efficiency experiments can be guaranteed with the implementation of high frequency precession, automated precession alignments. This also guarantee the high spatial resolution and also automated data analysis. And all of those can be done over a flexible field of view while maintaining a pretty fine probe. So this makes the ideal data for reliable orientation, phase mapping, or precise strain mapping. So with that, that concludes my presentation today. I'd like to share with you some upcoming webinars. June the 16th, we have Dr. Partha Das from NanoMEGAS talk about micro-ED. And also in the same session, Professor Simon Billage from Columbia University to talk about local structure at nanoscale and how to measure them. On July the 7th, Professor Gregory Thompson from University of Alabama will be talking about cross-correlative microscopy with precession electron diffraction. Okay, and so this photo was taken in Death Valley in a tourist spot called Racetrack. This is a pretty neat spot. I'll say a little bit more about it. So this is basically a flat, dried lake bed. It's about 2.8 by 1.3 miles long and wide. It's so flat that the difference in height from north and south end is only about 1.3 inch. But you can see, I'm not sure whether you can make out those traces, but there are quite a few rocks like this, just leaving traces behind them. So the movement, mysterious movement, actually has been resolved about 2014, I think. I will not spoil it for you. You can check it out if you're interested. All right, and with that, I'd like to thank you for your attention. And if there is any questions, I'd like to discuss.